Hi, I'm Ben Schreiber and welcome to Music Algo. Here I'll be showing you the selection sort analysis, which will show you how to analyze selection sort in terms of big O, memory, and runtime. And after this video, you may realize that selection sort is not usually the best choice for sorting a list of values, but it does have a nice property of stability. Anyway, after this video, you'll be ready for the selection sort song and code, so let's get started. Selection sort is an algorithm, if you don't know, that takes in a list of numbers as input. Its purpose is to sort the list from lowest to highest such that the lowest values are on the left and the highest values on the right in non-decreasing order. Here's the agenda for this video. First, we're going to review the algorithm. Second, we're going to do a runtime analysis of selection sort. Then we're going to understand the memory usage analysis. And last, we're going to give a brief summary of when to use selection sort. If I mention any concepts or vocabulary that you might not be familiar with, please check out the prerequisites section of musicalgo.com. So here's how the selection sort procedure goes. It first locates the smallest value from position 0 onwards or to the right. It then swaps that value with the value currently at position 0. Next, it locates the smallest value from position 1 onwards. It then swaps that value with the value currently at position 1. And it does this for all remaining positions in the list. So you can think of it in this way. It first finds the minimum value in the list and puts it at position 0. It then finds the second smallest value in the list, and because we put the smallest one at position 0, we only have to look from position 1 onwards. It then puts that value at position 1, and then finds the third smallest value, and because we know the two smallest are at position 0 and 1, it doesn't have to look at those, and it can look from position 2 onwards. And you can see the pattern. So it does this for all remaining positions in the list. So real fast, I'm just going to go over the procedure of finding the minimum value from a particular position onwards, because we're going to be seeing this a few times. When we find the minimum value from a particular position, we'll say I onwards, we create a place marker called min_pos that keeps track of where the smallest value is from position I onwards. We initialize min_pos to I, and then compare every value from I onwards to the value at the min_pos. Now, you don't need to compare the value at position I with the value at min_pos because they are the same, but we'll do it anyway because it makes the analysis a bit more clean, and in the end we get the same result. So real fast, we're just going to go through an example of finding the minimum value from a particular position onwards. Here we're finding the minimum value from position I onwards. And we're going to store a variable here that will keep track of the position of the minimum value that we've seen so far. We're going to call that min_pos, and initially we're going to set it to 0. So first we're going to compare the value at position 0 to the value at min_pos. They're obviously the same, so we move on, don't change anything. Next we look at the value at position 1. It is greater than the value at position 0, our min_pos, so we don't do anything. Next we look at the value at position 2. This is less than the value at our min_pos, so we change our min_pos to 2. Alright, so now we look at the value at position 3. It is less than the value at our min_pos, so now we change our min_pos to be position 3. Now we look at the value at position 4. It is equal to the value at our min_pos, so we don't change the min_pos. Last, we look at the value at position 5. It is greater than the value at our min_pos, so we don't do anything. And thus, 3 is where we found the minimum value at position 3. So when we analyze the performance of an algorithm, we use a notation called big O, which measures the performance of an algorithm relative to the size of the input list. So we're looking for a relationship between the size of the input list and how much time or how much memory the algorithm uses. And we can see that relationship in the graph below.
So the x-axis here is the size of the input data, and the y-axis is the amount of time the algorithm takes to run. So you can see that some algorithms have a constant relationship. The amount of time that takes to run is constant relative to the size of the input list. Others have a logarithmic relationship between the amount of time they take to run and the size of their input list, and so on. You can see there are a bunch of other relationships.
So we're going to do two analyses here. One, we're going to see how many steps selection sort will take, and another analysis we'll see how much memory selection sort will take. Once we have determined both of these amounts, we omit constant coefficients and remove any terms that are dominated as the input size tends toward infinity. So I'll show you what I mean. So say we determined that an algorithm took 2n squared plus n steps, okay? So we first omit constant coefficients. Here 2 is a constant, so we omit that. And then we omit terms that are dominated as the input list size tends toward infinity. So we keep on plugging in larger and larger numbers for n, and whichever of the terms increases faster, that's the dominator. That's the one we keep. The ones that increase slower are the ones that we omit. So here if we plug in 100, then 1,000, 1,000,000, and so on,
we're going to notice that the quadratic term increases a lot faster than the linear term. So if we looked at a graph of n squared versus n, we're going to notice that n squared gets larger a lot faster than n. So we can omit n because it is being dominated by n squared. So now all that's left is n squared, which means that this algorithm must run at O of n squared.
So there's really nothing in the selection sort procedure that would cause it to perform better on some lists than others of the same size. Now this means that it is not adaptive. If it were adaptive, some lists would be better than others, even if their size were equal. So insertion sort, for example, does a lot better on lists that are almost sorted, whereas selection sort will do the exact same thing whether the list is in reverse order or doesn't have a single element out of order. So when we analyze in terms of big O, our unit of time here we're going to say is comparisons of values. So that will be our y-axis, the number of comparisons selection sort makes, on a generic list of size n. So how many steps does selection sort take to execute? Well, first it finds the minimum value from position 0 onwards. This will take n comparisons. So when we do this, we set the minimum value initially to be the one at position 0. And then we compare it to each value after, so to the right. If a value is less than the value at position 0, we recognize it as the new minimum and note where we found it. So next we find the minimum value from position 1 onwards, which will take n-1 comparisons, since we know the minimum value is at position 0. And we find the minimum value from each other position onwards and put it at the respective position. So for every single position that we've done this for, we will total to n plus n-1 plus all the integers in between n-1 and 1 comparisons. So we can express this quantity using summation notation, and it is known as a partial sum of the natural numbers, which amounts to n times the quantity of n plus 1 divided by 2. To show you what I mean, let's look at an example. Here we have the list 3, 6, 1, 4, and we're going to use selection sort to sort these values. So first we're going to find the minimum value from position 0 onwards. We're going to look at the value at position 0, value at position 1, value at position 2, and the value at position 3. So 4 comparisons. After making those comparisons, we will confirm that the minimum value from position 0 onwards is at position 2, so we're going to swap the value there with the value at position 0. Now we find the minimum value from position 1 onwards. And to do this, we're going to look at 3 positions: the value at position 1, the value at position 2, and the value at position 3. We're going to discover that the minimum value of these 3 values is at position 2 and swap it with the value at position 1. So here we made 3 comparisons. So after that swap, the state of the list is 1, 3, 6, 4, and now we're going to find the minimum value from position 2 onwards. So here we're going to look at 2 values, the value at position 2 and the value at position 3. So we're going to make 2 comparisons here. And after making those comparisons, we're going to discover that the minimum value from position 2 onwards is at position 3. So we're going to swap the value at position 3 with the value at position 2. Continuing on with the procedure, we're going to find the minimum value from position 3 onwards, and that's going to take 1 comparison. And now the list is sorted. So you can see that we made 4 plus 3 plus 2 plus 1 comparisons. So this will amount to 10 total comparisons. And we want to see that this is consistent with our formula that we found earlier, that selection sort will make n times the quantity of n plus 1 divided by 2 comparisons. So if we substitute in 4 for n, we can see that this will make 4 times 5 divided by 2 comparisons, which amounts to 10. So this is consistent with our finding previously that selection sort will make n times the quantity of n plus 1 divided by 2 comparisons. So before we get any further, let's just gain a feel for why the partial sum of the natural numbers equals n times the quantity of n plus 1 divided by 2. So here we have the number of tallies we made while counting the number of comparisons selection sort makes for a list of size 4. On top of these tallies, I've overlaid a 4 by 5 grid. In other words, this is an n by n plus 1 size grid. So you can see here that 10 of the cells have been filled with tallies. The other 10 are empty. So if this is an n by n plus 1 grid and half of the cells have been filled with tallies or comparisons, then we know that the partial sum of n plus n minus 1 all the way down to 1 is going to be n by n plus 1 divided by 2, because half of the grid cells are filled. Now here we had n equal to 4, but I think you can see inductively that this sort of reasoning will work for any whole number positive value of n. So if we respell this sum, we multiply n times n and n times 1, divide that whole thing by 2. So that and this, they're the same thing, just respelled. So now I'm going to split this into 2 different terms. Okay, so now I'm going to remove the constant from both terms. 1/2 is the constant in each term. And now we see which of these terms dominates. So if we keep on plugging in larger values for n, we note which term increases faster. That's going to be the quadratic term. So we can omit the linear term. And thus, we have determined that this algorithm runs at O of n squared. So in this video, I won't get too deep as to why we drop constant coefficients in non-dominating terms. But I will give you the quick and dirty answer, and that is, in these asymptotic analyses where we care about the limiting behavior or the behavior as our input size gets larger and larger and larger, constant coefficients and non-dominating terms become negligible. So now for the memory analysis. How much computer memory does it take to execute selection sort, excluding the memory needed for the list itself? So in these sorting algorithms, we're always talking about auxiliary or extra memory, because
it's a given that it will need to store the list that we wish to sort in its memory. So, when checking for the minimum value from a particular position onwards, we need to store where we found that value. And we're also going to need to store two loop counters, one that keeps track of the position we're finding the minimum value to the right of. That's going to be the outer loop or the I loop. Another that actually loops through the positions right of it. That's the inner loop, or informally the J loop. Well, none of these three variables will require more or less memory based on the size of the list, and therefore selection sort requires constant or O of 1 extra space. So if we want to be extremely loyal to our procedure of finding big O, we're going to say that there are three values that we store, and we can express that as 3 times n to the 0 because n to the 0 is going to equal 1. So we omit constant coefficients. 3 is our constant coefficient. Thus, this will require O of 1 extra space. So when is selection sort used? After researching it myself, I've found that it is mostly used for educational purposes. However, it is not too slow on lists of smaller size, around 10 to 20 elements, and because of this, it can be used to complement divide and conquer algorithms, sorting algorithms like merge sort and quick sort. So these algorithms, the divide and conquer ones, they break the list down into successively smaller pieces until they can't be broken down anymore, so till the pieces are of size 1. Now, instead of breaking them down that much, you can actually call upon selection sort once you've broken the list down into pieces of, say, 10 to 20 elements. And selection sort will sort those elements, and you can return from the recursive call. Here are the takeaways from this video. First, selection sort is not adaptive. It performs the same on lists of equal size. It runs at O of n squared quadratic runtime. It uses O of 1 or constant memory. And in practice, it is best on lists of smaller size. So I hope you found this video very educational. Now you may be ready for the selection sort song and code, which has the facts from this video, and the selection sort pseudocode, which will help you execute or implement selection sort in any programming language. And if you have any feedback for me on this video, I'd love to hear it. If you really liked the video, please share it with your friends. And thank you for watching.